In the previous video, we looked at Horrorboard as one of the uh, tools that can actually be used for distributed deep learning. So we also took a look at how that actually helps solve three of the challenges that deep learning on big data faces. So in this video, we will look at the fourth challenge. So for those who need a refresher, let's just take a look at what the fourth challenge was. So that's related to the problem of how do you take deep learning models, which are very large in size typically, and run this in a streaming sense on streaming fast moving data, but without the streaming framework requiring a fresh invocation to load the data model, load the deep learning model again, all over again. Because the size being large means that the act of loading the model for the first time becomes really expensive. So if you keep having to load it for every record of scoring, especially for fast moving data, that becomes a absolutely non-starter, right? So what is available as a way to work around this? So let's take a look at why this problem occurs in a bit, and then we'll take a look at the solution itself. So Spark is JVM based. It's a Java based architecture, whereas most of the DL frameworks, in fact all of them that we use typically, are Python based. So the ability to exchange the data between the two is actually key, right? Because we're going from Java to Python. Now, data exchange, when it comes to batch data, you can just take a bunch of data from JVM and load it into Python, right? And then using what's called as a remote procedure call, or RPC, and then you can do the work same in the other direction as well. As part of Horrorboard, there is something called as Petascale. Petascale does this in a way that's very scalable and easy, so that you can go from data frames to the TF records or Parquet data formats that's necessary for the deep learning frameworks to work, and vice versa. But that's for batch data. What about streaming data? Right? When it comes to streaming data, you have to now think about how do you take each data element and send it across. So there, Petascale will not actually help you. What could be more beneficial is to vectorize the data such that you can do your own optimizations on top of it. So one of the main ways in which you can vectorize data is, of course, using Pandas. But to work with Pandas, you need the ability to think in terms of Pandas custom functions, right? So that Pandas custom functions is something called as the Pandas user-defined function, basically with lambda functions in Python. That needs to execute within a PySpark context, right? So, long story short, Spark has evolved the mechanisms to actually allow Pandas UDF style support, such that you can access the data within Spark like a data frame, but you can work on top of it as though you would work on top of it using Pandas, which is basically with vectorized data operations which allow for optimizations. And to do that, it supports the ability for you to define your own functions. And that Pandas UDF support is what we're going to spend some time on with an example. Now, the parallelism that is there, which is available for streaming frameworks where you have multiple executors, is typically model agnostic. So every scoring invocation will trigger a load of the model afresh. So for a small model like a decision tree, this doesn't make a big difference, but large size deep learning models, it becomes problematic. So what we will do to handle or solve for this problem is use the same Pandas UDF feature, vectorize the data, send it across to the Python process, and in doing so, make the Python process load the data, or rather load the model once at the beginning of the setup of the process, so that every invocation that happens on a regular basis, like as part of streaming invocation, as part of every single record, uses the model that's already loaded in memory, right? So in effect, I've taken this model scoring operation and actually split it into two parts. One, which is model load, which can be done once per Python process, and model scoring, which happens once per data element, which is every data element in real time. Now, the model load itself can be split up as something that happens once per Python process, and that Python process can be set up once per executor, at the beginning of the particular job. So go back to your Spark streaming, go back to your data flow. You'll notice that the streaming is a long-running job. It's actually a never-ending job, right? So which means at the start of the Spark streaming execution, for the first time that the Spark streaming executes, the Spark executors come up. As part of that, the Python processes also come up. So it's the first execution which incurs the overhead of reading the model, the deep learning model with its enormous weights, right, from disk and loading it into memory. And once it's done, from that point on, it's a long-running job, right? It's always available. The Python process is always on. So every single scoring job that runs after that, or scoring request that runs after that, can leverage the fact that the model is already loaded into memory by the Python process. So that's what we will use as the solution for solving for this problem. So with this, let's take a look at this example in a Google Colab environment. So you can use this as an alternative to GCP as an example. Colab allows me to visualize like a Python Jupyter notebook, right? So I'm going to use this Jupyter notebook for working with this PySpark code. So let's go through one by one. The code with the Python notebook is self-contained, so you'll be given access to this Jupyter notebook as part of this week's lab. So just try it out for yourself. Colab is free as well, by the way. Okay, so we are now going to take a look at what's happening within this code, right, and look at how the Pandas UDF is used. So first and foremost, the problem statement we want to solve for, let's take a look at that. We're going to work with this data which has photos of flowers, right? So let's take a look at what that entails. I've downloaded the data. You can also download it yourself. It's got a bunch of these folders: daisy, dandelion, roses, sunflowers, etc. And within each of these folders, there are these images available to you, right? So these are two examples of sunflowers, right? Likewise, there's an example of rose as well. Okay, this is a very interesting example of rose. Yeah, so there's also an example of a rose. To a human, we might be able to say these two are roses or these two are sunflowers, but how do you get a machine to actually do this? So what we will see as an example here is, we will take an example of a pre-trained model, because we want to make it run fast as for this demo. So we're going to use the mobile net version. So a pre-trained image recognition model, which is state of the art, right? Take that, apply that against this specific set of downloaded flower photos that we are using, and invoke it using Pandas UDF structure, so that we understand how this entire Pandas based invocation of deep learning scoring happens. Once we know that, and this is a batch program, by the way, right? What I'll show you is a batch example. You can easily convert this into a streaming example, right? By having the data stream through something like Kafka, and then you're reading from there. So let's take a look at this. First and foremost, I just get the data downloaded. Before that, some standard imports, of course. So once I have the data there, I load it up and I read it as a data frame, right, with its path. So the format is actually a binary file, because these are JPEGs that we're talking about. Okay, so then I've got a bunch of things that I want to evaluate as standard matrices, standard data processing or transformations, you can think of it that way. So one is, given a particular file path, I want to extract the label attached to it. The label is going to be the name of the folder, right, in which the files are present. So in this case, daisy, dandelion, roses. So that becomes my supervised set of categories, right? So that's my label data. So that's what extract label corresponds to, and I've got a definition of this function. Extracting size is basically the size of the image, right? Size of the image here is like 31 KB, 100 KB, etc. etc. There's a wide variance in terms of the size. So I've also created a Pandas UDF here as an example, which extracts the dimensions of the of the particular UDF, of the particular image, but using a pandas execution. So the way I use the pandas execution or trigger the pandas execution is by using a decorator. The decorator looks like this, right? I just say at the rate of pandas underscore UDF, define the schema that I'm producing as the output of the UDF, and that will automatically let Spark know that I have to use the pandas UDF. I have to use pandas for executing this. So that decorator is available as part of a implementation of a project called as Arrow, Apache Arrow, and Spark is using Arrow behind the scenes. Okay, so what I'm doing here is just extracting the size of the image in terms of width and height. So what does width and height refer to? So let's take one of these images. Yeah, so the width here is 320 pixels, the height is 213 pixels. Right, so width is 320, the height is 213. That's what this is referring to. Okay, so from the images data frame, right, I just extract out the label that we just spoke about, the size as well using the pandas UDF, and then I also get the some other metadata attached to the images, like what is the path, what is the modification time, what is the content, etc. Anyway, those are lesser important. Now let's take a look at actually what's happening with respect to the deep learning code and the pandas UDF scoring. So in this case, I'm going to use Torch, which is PyTorch, and from PyTorch there are standard utilities available for dealing with image data. So they are called as dataset, data loader, etc. And the pandas UDF itself is available as part of PySpark that we spoke about. So from PySpark SQL functions, we import pandas UDF and pandas UDF type. Okay, so what we will do first is we will define what is the base data set into which we will load up all the images in a transformed manner. That is what we call as the ImageNet dataset. Notice that ImageNet is not what we're dealing with here. ImageNet is what the pre-trained model was trained on, right? And what we're doing here is we're just taking that pre-trained model and applying it against the Flower dataset. But because of transfer learning, a lot of the in fact, in this case, transfer learning is not required. Sorry, the pre-trained data, a pre-trained model will directly apply on the Flower data as well, right? Without any changes. So the training happened using this ImageNet data structure. So that's what I'm defining here as a class. So it's a specific way in which I want to transform every image, right? So basically, I want to resize all the images to 256 pixels, center crop, etc. Convert it to a tensor, normalize certain values, etc. So with this transform done, I'll have a standard representation for an image, right? So I don't have to worry about different images being cropped in different ways, etc. I'll come back to this ImageNet model UDF in a bit. The main thing that I'm talking about here is the predictions. How do I get the predictions? I take the data frame, the DF data frame here refers to the set of images, right, along with the label, the supervised label. That's this data frame, DF, that I'm talking about. To that data frame, I apply a mobile net deep learning network. It's one of the pre-trained networks. How do I apply it? I apply it using a UDF. I'm calling that UDF as the mobile net v2 UDF. That mobile net v2 UDF takes as an input parameter the content. The content is basically the entire binary file of that JPEG, which is every single one of these pixels that you see, right? So that's the content. How do you know that's the content? That's what is given to you as part of this format of binary file when it reads these images. Right? You can look it up online, right? What does format binary file mean for Spark? Okay, so I'm giving the input as the content, which is basically the image binary data itself. The mobile net v2 UDF will provide a prediction. So the prediction is going to be a new column in that same data frame. So what I'll do is I'll just append that column to the data frame. Once I append that column, I'm going to call that column as prediction. Then I can display what should that, basically then I have my answer. I can just display that and take the answer. So in this case, for instance, for image 11939491, the prediction is it's Daisy. Right, the 11931491 corresponds to this file name that you're seeing here. Okay, so the crux of what is happening here is happening within the MobileNet v2 UDF. So let's take a look at that. What is the MobileNet v2 UDF? That's defined here. It is defined as an ImageNet model UDF, right, which has a custom lambda function, which is basically a function by itself, right, which is a user-defined function by itself, and that custom lambda function is a pre-trained MobileNet v2 version, MobileNet v2 model. Where am I getting the MobileNet v2 model? I'm getting it from models. What is models? Models is one of the pre-trained modules available within PyTorch. So from that models, I'm getting MobileNet v2 as a pre-trained network, and in fact I've defined the pre-trained variable to be true, so that there is no retraining that's triggered accidentally also, or that it just indicates to the deep learning program that I don't need to worry about this in terms of training again. I'm defining this as a lambda because it's a custom definition. It's a custom UDF that I'm invoking here. It's a custom transform that I'm invoking here. So the parameter is well understood, which is just the MobileNet v2 pre-trained model. So, but what's happening within ImageNet model UDF? So notice this. The MobileNet v2 UDF itself is a function, right? It's actually not a data frame. It's a function. It's a user-defined function. So that user-defined function itself is created by another function. So the creation of the function is controlled by the ImageNet model UDF, right? That creator function takes as parameter the pre-trained model, which is MobileNet v2. What is the creator function doing? The creator function takes a model function, right? So the model function is basically an ImageNet model in this case, wraps it into a Pandas UDF, right? So that it can operate on vectorized data in a standalone Python process, and therefore be eligible for the optimization of loading the model only once per Python process, using it multiple times repeatedly for as many data sets as available in the scoring, right? So that's the reason why we're doing this. So I want to wrap this ImageNet model, in this case the MobileNet v2, into a Pandas UDF so that I can make the prediction. That's what happens here eventually, right? I'm returning a Pandas UDF, which means I'm returning a function. So the creator function is returning a function because it's creating that function, and that return function is of Pandas UDF type. The return type is a scalar iterator. Scalar iterator is basically an iterator over scalar values, and the definition of what is going to happen in that function is a predict, right? Is defined in predict. What is predict? Predict is defined here, right? Okay, so what is in predict? Let's take a look at that. The predict will be fed an iterator of data points. So remember, the function is going to be used in the context of deep learning scoring. So it's going to be fed a whole bunch of these images as part of an image data frame. So that entire set of image data frames, rather than the entire set of images in that data frame, is converted into a content series iterator, which means it's an iterator of binary content series, right? So that's what I'm going to deal with as the fundamental data points that I'm now going to predict on top of using Pandas. So one of the first things I do within the predict is load the model into memory. So I've got the model defined for me as a parameter, which is MobileNet v2. So that's this model function parameter. By calling model.eval, I make that model get loaded into memory, right? That happens at the beginning of the predict. So when the Python process executes in a particular executor, the predict function gets called for the first time. The model gets loaded for the first time. From that point on, all the data sets that's available in the data frame gets invoked in an iterator. So the invocation of the model within for every single one of those images happens within this iterator. It does not require a load again, right? So that's the key here. I load it once. After that, I use it again and again for every single data point, every single content, which is the binary content of an image. Every single one of that, I can just use the same loaded model again and again and again. How do I use it? So here we have to look at specifics of how PyTorch deals with image data. You have to convert it into the same format using the ImageNet dataset. The dataset itself is actually a list of images. Then you use a data loader. That's the way that PyTorch works when it trained the model in the first place. And then for each image in that batch, it went and did a prediction. The predictions themselves were, the prediction is basically this, right? It just took the image batch, which is basically the set of binary content, and then did the prediction on top of it. That predictions itself is an array. So then I can just decode that and make it into a predicted labels array, and I can yield that as a data frame, a pandas data frame. A collection of those pandas data frames becomes my final series. That series is converted back into a Spark data frame, right? By the Spark integration with Pandas UDF. So there's a lot of backend data processing or data exchange that's actually happening here. That's handled by Apache Arrow. You don't need to worry about it. What you're yielding is just a Pandas style data frame that gets automatically converted using the return type that you specify, such that you can then access it using a Spark data frame kind of syntax. So you can, this set of examples of how the image is processed, what happens behind the scenes for ImageNet training, etc. Those are advanced topics. You'll probably read about them in your deep learning course if you take it. Or if you're curious, you can just Google about it and look it up yourself. The key here is notice how the Pandas UDF gets created. It's created by a creator UDF, which takes the input as the type of pre-trained model that you want, and within that it creates the Pandas UDF. But the way it creates it is by first loading the model into memory. It does it by just invoking the eval function, and then from that point on, it deals with the series of data that's available in Python, and for that series it invokes the appropriate transformations to those images and then returns the predictions in the form of a Pandas data frame. Spark takes care of the conversion between the Pandas data frame and the Spark data frame. So with that, we've got the final predictions done. The good part is with MobileNet now, we can actually take this and run it in a streaming fashion, and each executor instance will run pretty fast as well, because MobileNet itself is a highly compressed ImageNet algorithm, right? Okay, so with that, we've come to a conclusion of the ways in which you can do deep learning on big data. So we've looked at 4 challenges. We've actually solved for all 4 of those using two tools. One is Horobot, and the second is the Pandas UDF integration. So net, just within the Spark library or Spark environment, you now have access to deep learning using Horobot, not just for scoring but also for training. And specifically for scoring, you have access to Pandas UDF as a mechanism to ensure that your deep learning models are still optimally executed for every scoring invocation, and therefore you can use it for streaming computations as well, as opposed to just the batch computations that you see here. Okay. Okay, so with that, we've come to a close of this week's lecture. Thanks very much. As one final lecture, we will look at recapping the entire course across all of the different modules that we have done across the weeks. Thank you.